Good morning, everyone. First of all, it's my pleasure to be invited for the keynote in this very interesting and exciting workshop. Today, I'll be highlighting some of the challenges and opportunities in a very broad area of communication and sensing for autonomous systems. In particular, I would like to present my vision and some of the research work which is ongoing in our research group, which tries to look at what sort of communication and connectivity requirements stem from future applications of robotics and autonomous system, and also tries to figure out that given enormous proliferation of robotics and autonomous systems in the society, what sort of a new communication and networking paradigms we can enable by harnessing the power of these mobile platforms mainly. In exposing these two different elements of research, I would try and connect and answer this question that how does this connect with next generation of wireless connectivity. So for example, at the moment there is a lot of talk in the community about 6G wireless network. What does it mean for robotics and autonomous system type of application, and how can we basically harness power of 6G to enable these type of applications is something which we are going to explore during this talk as well. So before I dive into the technical part of this talk, a little bit about myself. I am an associate professor of communication and sensing at University of Leeds. Uh, Okay, so my areas of expertise are mainly in the wireless communication networks. I look at co-design of communication and control for robotics and autonomous system type of application. And I also I'm interested in spatiotemporal modeling of such networks as well, using stochastic geometry, random graph theory, machine learning, and signal processing type of type tools mainly. Currently, I'm leading several EU and EPSRC projects. A couple of them are listed here, which I'm going to talk about today in my talk. One of these projects, which is a EPSRC program grant on pervasive sensing for buried infrastructure, we are trying to develop small robots or teams of robots, or you can call them swarm robots, to inspect buried infrastructure. And I'm co-leading the communication and sensing team there. On the communication end, it's a really harsh environment. So the main challenge is how do we provision connectivity in such a harsh environment as well. So I'll bring some of the learnings from that project into today's discussion as well. Okay, so let me move on. A very brief outline of this talk. As I said, in the first part of this talk, I'll be covering topics which look at how communication and connectivity is changing in response to service, robotics, and autonomous type applications. In the second half of this talk, I will be discussing how robotics and autonomous systems can be employed to service communication and connectivity in future generations of wireless network. Generally, then I'll conclude with some of the key takeaways from this talk towards the end of. Every year, we ask an oracle to predict what future holds for technology. Forecasting of future is an artistic yet scientific experiment. However, in my opinion, it's best left to the technological firms who employ a massive amount of brain power to work out technological roadmaps. As academics, we are naturally carrying out research in these areas, so we have some understanding of how technology is moving and what sort of new avenues technologically are viable in short and longer term. So one of the firms which makes such technology predictions is Gartner, and most of us are familiar with Gartner's hype cycle, which tries to map different phases through which a technology basically uh, passes through till it gets matured and adopted by the industry. Now, if we look at Gartner's impact radar for 2023, it tries to map what are the key technologies which are going to have maximum impact in short term, and what are the technologies which have medium to long term impact, essentially. So one of the key technologies here, which features this impact radar, is the Edge AI, which is becoming very sort of uh, pervasive in different IoT applications, mainly due to frameworks like TinyML, which allows us to compress the models and machine learning models and execute it on Edge. The implementation of Edge AI, especially combined with computer vision and different types of sensing modalities, such as RF sensing, for example, brings about really transformative amount of change in the application areas as well. So as most of us in wireless communication community are aware of joint communication and sensing, joint communication and sensing will hopefully exploit this Edge AI and machine learning capabilities to develop more sort of deployable applications in different spheres of life, including healthcare, transportation, rural connectivity, etc. Obviously, with increasing proliferation of AI, increasingly there is a ask to deploy this AI and machine learning models on devices which have very low capabilities, which have very restricted amount of energy access. Typically, we want these devices to run several layers on a single coin cell, or in some cases on AAA batteries, for example. So the power density of the battery itself hasn't improved over last few years. There is a lot of ongoing research on energy harvesting, on recycling the amount of energy present in the ambient environment and exploit that. But even with all those energy maximization techniques, we need to look at how we can compress the machine learning models which we execute on these Edge AI devices as well. So in short to medium term, research on model compression becomes really important as well. So once you have embedded this intelligence into lots of sensors and actuators and deployed at scale, that enables you to create digital replicas of physical machines and processes. And if you connect these digital replicas together, you get what is frequently known as a digital twin, which allows you to basically do a forecasting over a time horizon and do things like proactive maintenance, predictive repair, optimize the operational efficiency, minimize the energy consumption, and several application specific things as well. So that's why digital twins are gaining popularity because they go hand in hand with IoT and Edge AI. Obviously, when you're trying to run a virtual replica of a physical process or a physical entity, you try to combine the actual state information which you are capturing using your sensors and your predictive model in some sort of a way. And that sort of way of approaching or combining model-based data and sensor data to drive intelligence over space and time generally falls into spatial computing category. So we can see spatial computing will evolve as a big topic in future. Obviously, you do not only want to embed intelligence in individual sensors, but you want to exploit this intelligence scattered around different smart entities in sort of a unified way. So you need to connect these things in some sort of way where 6G will play a critical role. Now, the impact of 6G will be quite high. What we need to think about as a community is that when we're connecting these sort of things, what sort of connectivity requirements we should be considering. Do the applications which we are looking at warrant ultra reliable low latency connectivity, or should we be thinking about different traffic classes? For example, when 5G came up with these three traffic classes, massive machine type communication, EMBB, enhanced broadband class, and the ultra reliable low latency connectivity services. But these three classes do not capture adequately some of the use cases which were trying to address um, in robotics and autonomous system domain specifically. And there is an increasing talk in industry about red cap devices or reduced capability devices, and the traffic class which can serve as red cap devices, sort of a hybrid between these three essential elements of 5G. So then there is a discussion on how 6G can basically enable these sort of service classes as well. We will discuss a little bit on that in a few minutes time. Okay, so what we are trying to understand is how these technologies which I mentioned are a key focus in our research group connect to robotics and autonomous systems sphere itself. So let's take a step back and look at how we define robotics and autonomous system. So I'll take a definition from, I mean, there could be a variety of ways of defining robotics and autonomous systems, but I'll take one definition from this report which was published by UK government some time ago. And it describes robotics and autonomous system as a physical embodiment which can take actions independent of human control by sensing, reasoning, and adapting to a given situation or an environment. So if we think about where the line is set between a traditional equipment and a robotics and autonomous system, it's the capability to make decisions autonomously and sense the sphere of operation in which exists. And that this sensing capabilities of sphere of operation then basically brings about operational environment awareness, and that's where AI or machine learning plays a crucial role to enable translating these operations or these inferences into decision-making capabilities, for example. However, if we try and take this definition and break down the whole operation of robotics and autonomous system into four discrete components, mainly any robotics and autonomous system would need some sort of sensing capabilities. It would need some sort of a perception mechanism. And based on that perception, it will drive its cognition, which is what should I do when I encounter this sort of situation? Because when you're sensing your operational sphere or sphere of your operation, I should say, then there are a huge number of variations in and dynamic factors in that environment. So each one would lead to a unique sort of a representation in terms of its of a perception, and then that needs to be mapped onto certain concrete action in terms of cognition. And that cognition action will basically impact the physical world itself. So it could be just a maneuver of a robotic arm, or it could be a mobile robotic platform trying to navigate a certain trajectory, and that modifies the physical world itself. So you have this feedback loop through the sensing again, and you would have a new sort of representation or perception of the world, and then on that basis you decide what to do next as well. So this is a continuous cycle which involves sensing, perception, cognition, and action. Now, two of these elements sit in the physical world, such as sensing and actuation, and two of the core elements of implementing a robotic and autonomous system, such as perception and cognition, sit in a digital world. So essentially, a robotic and autonomous systems any robotic and autonomous system tries to blend physical and digital world in a closed loop manner so that a particular task can be completed by that particular platform. Okay, so taking this further forward. Okay, so when we are discussing how we connect this digital and physical world together, we should be conscious of what does that enable us to do in terms of economic impact. And if we look at these sort of economic forecasts, it seems like that a robotics and autonomous system is poised to contribute 4.5 trillion per annum by 2025. That's a huge contribution to the society. If we look at the UK forecast, for example, by 2030, we can see that the market size would be 3,500 million. And the majority of that market share is captured by mobile robotics type of applications, which require connectivity and compute to be present in some form to drive their autonomy, as we will see in the later discussion. Now, essentially, what we're talking about is the combination of communication, controls, and compute capabilities, as we know in the traditional cyber physical sense. And these three areas themselves are going through a transformative changes in terms of research at the moment. So, for example, we can pick any two areas. So let's pick up communication and controls, for example. And there are some very interesting research areas at the intersection of these two, which we explore in our research group. For example, how do you do task-aware communication? So if you are trying to design a controller which basically takes your robot from point A to B, can you take communication constraints into account and do a trajectory planning, which basically enables your robot to navigate its environment while being connected all the time? There could be problems such as RAS for communication systems. So how do you use control capabilities to position RAS optimally, for example, such that you improve the communication network's coverage and capacity performances, for example. So these sort of areas require you to co-design communication and controls together, for example. Then there are other areas such as if you look at compute and communication, for example, there is this question of edge for cloud continuum. Where do you place the intelligence? How much intelligence should be placed where, and what sort of latency do you get with such a split? Then there is a question of how can you ensure that the intelligence is where it needs to go and it executes in a similar environment to what it is meant to be executing in. So what I mean by that is that you can write a machine learning code on your computer, and then you want to scale it up to thousands of nodes. And how do you scale it up? And this mainly relates to infrastructure as a code or infrastructure technologies such as Kubernetes, Dockers, or how do you orchestrate these sort of cloud native implementation of these algorithms as well. If we look at computing and controls, then there are areas such as learning-based control, for example, that how do you exploit machine learning to do the controls where you don't have that much information about the model, or the model-based learning controls is not tractable. You have edge computing to enable such learning-based control paradigms, for example, so using reinforcement learning on the edge, for example. And then if we look at the intersection of all these three areas, we come up with this main theme which I'm talking about today: communication for robotics and autonomous systems. So the main interesting challenge lie at the intersection of these three different areas and touch upon all these different aspects which I've been discussing so far. Okay, so in first part of this presentation, I'm just going to talk about what are the requirements in terms of future communication systems and connectivity for robotics and autonomous system, as I have highlighted. And let's start with this vision for 6G networks. So one of the European projects, very famous European projects, is HexX, and currently HexX2, for example, which presented early vision for 6G. And it sort of identifies three spheres of operations for 6G, mainly what the world we live in, so physical world, and then creating somehow digital replica of that world, so a digital world, and basically creating another sort of perspective to that is that the 6G is not only supposed to deliver key performance indicators, but it is supposed to help a society to extract maximum value out of technology as well. So there are key value indicators associated with 6G as well. And that sort of falls into human-centric computing and communication as well. So it's basically trying to merge this physical and virtual world together. This whole idea which I presented already exists in case of robotics and autonomous system is now sort of being adapted by 6G community to enable use cases which allow you to basically extract maximum value from the physical processes and physical world, and try and build digital replica of everything at scale, and try to be proactive and increase the operational efficiency of your infrastructure, of your different different process dynamics as well. And in doing so, in creating this sort of a digital twinning based control, and creating this sort of augmented intelligence at scale, we want to be cognizant of the human factors. So we need to take into account things like privacy preservation, things like resilience, how do we embed security and trust intrinsically in these processes as well. And when we can connect these three different sort of pillars together, physical world, digital world, and human-centric computing in some sort of a way, then we can enable all sort of different types of applications, including robotics and cobots, telepresence, massive twinning, enabling sustainability across the society, and all these type of application. I won't go through all of this in detail today. Okay, so this is a really sort of a technological perspective to what 6G could look like, but we need to ground our vision into some sort of a realism as well. And how do we do that? To basically come up with more realistic estimate of what 6G could end up being, we conduct something like pest analysis. Pest analysis looks at what are the political factors, what are the economic factors, what are the social factors, and what are the technological factors which are sort of emerging in a way that will shape the connectivity paradigm for the future. So if we look at things like social factor, sustainability and energy efficiency are the two most important factors. There is a widening digital divide. And when we talk about embedding native AI into networks, there is a lack of trust in governments in using data appropriately by civilians as well. There is a skills gap of how these systems, which are increasingly complex due to cloud native implementation, will be implemented as well. And some of these social factors contrast with the economic factors, for example. So if we look at economic factors, each year operators globally spend approximately 17 billion on energy. Energy consumption is responsible for about 15 to 40% of OPEX for mobile operators. And mobile networks are expected to transfer more data going forward. So more than 90% of the network costs are spent on energy, consisting of fuel and electricity consumption. Also, recent study shows that 60% increase in the total cost of ownership for 5G deployments, even when using conservative estimates. Hence, it's natural to assume that 6G systems will have even higher TCOs, as achieving cyber-physical continuum via connected intelligence require further investment in the network itself. So 6G telecom networks are forecasted to connect around 50 billion devices by 2031, creating a massive web of interconnected devices. However, this comes with increasing worry about increasing the digital divide itself, because the cost of affordance of connectivity might go up as well. And we're trying to reduce the energy consumption of 6G to be environmentally sustainable and also reduce the total cost of ownership. But at the same time, we want to run more sort of a native machine learning payloads or AI payloads on the inside the network itself. So as you might be aware of, the Open RAN architecture, for example, allows you to have XApps and RApps running in RIC, for example. And that comes with the energy implications itself as well. So there is a trade-off on how do you increase the intelligence to reduce the complexity of the management, but at the same time make the networks green as well. Then there is a sort of a contrast when we look at resource efficiency versus openness of the network itself. So if if sort of the whole network functionality was implemented by a single sort of proprietary vendor, resource efficiency can be made really good, because you know what's going on in a certain element versus how can you optimize resources depending on the dynamics of that component, for example. But when you try and implement open networks, you try to develop interfaces which are basically allowing interoperability between different components. But these interfaces are not often designed while considering resource efficiency in end-to-end manner as well. So we need to consider that as well, mainly. And as we talk about open networks and open standards, there is a political pressure of avoiding vendor lock-ins and not using a particular type of vendors or particular, only a certain types, certain class of vendors, for example. So we need open, there is a push towards open standardization, but we have to be conscious and cognizant of all the legacy code which exists in RAN space already. So how do we migrate that sort of knowledge into open? Implementation becomes a challenge as well. And then, unlike previous generation, there is a worry of fragmentation due to geopolitical reasons as well. Again, if we pick up things like technological factors, which are okay, AI is basically gaining a lot of momentum. We can do a lot of interesting things if we implement AI within the RAN. Then there is this question of how do we ensure trustworthiness and transparency in the network as well. So we, for example, we can mine information about the mobility to do proactive resource allocation and handover management and whatnot. But how do we obtain consent from the user for such a research as well? So if you pick up any of these elements and compare and contrast them, so you can pick political factor and an economic factor and contrast them, you'll find a trade-off. And these trade-offs are basically generating interesting research challenges for 6G research. And in my opinion, that's where these are the challenges which 6G would address from technological perspective as well. Okay, so moving forward, um, one of the main ways of addressing these challenges is through, uh, obviously we are talking about native integration of AI from technological perspective in the networks, and we know that somewhat if we crack how to make this AI green, then that can add a lot of value in terms of managing the complexity of the network itself. And one such architecture which allows us to do that is Open RAN architecture. In Open RAN, you have different components. You have ORU, ODU, OCU. I mean, I won't go into the details, but the main idea is that you will be able to execute near real-time and non-real-time applications in RAN intelligence controller. And these applications can be implemented in a virtualized, disaggregated manner. So basically, we can use things like container network functions or virtual network functions, or we can also use things like FAST, for example, or microservices uh, or Lambda functions, depending on which community you are coming from. And there's a lot of work going on RAN transformation and implementation of these XApps and RApps in an intelligent manner. So our vision is that the problem with this approach of doing machine learning through um, in the Open RAN and in the RIC and XApps and RApps is mainly that there is a lot of suggestion of doing reinforcement learning within the RIC itself. However, doing any such learning will lead to deterioration and user experience. There's a lack of transferability. So if you are learning in a RIC, in a particular XApp, certain behavior about users connected to a certain DU, then that learning is not transferable across the network at other deployment sites, for example. And since it's not transferable, there is energy cost, energy implication of this as well. So every site is trying to retrain using reinforcement learning, which means that you are burning a lot of energy. Where if you had shared and collective knowledge base, you could have avoided such energy penalty. There is a lack of context, so you're learning to do something, but you don't know the context of what you're trying to learn. So you're not aware about the semantics of the network, and if you're not aware about of the semantics, you can't apply what you've learned generally and reuse it across different problems, for example. And again, then as you saw in the Open Run architecture, you can do learning in the DU, you can do learning in near real-time RIC, or you can do learning in non-real-time RIC, and these all have different temporal scales. So how do you deal with data which sits with such a temporal variability in a collective manner so that your learning does not have temporal and representational biases in longer term? So the idea for which we are trying to pursue in our group is basically based on building network digital twins, a virtual replica. Since the implementation is disaggregated and distributed and virtualized anyway, it's easier to create a replica of a physical system in a virtual environment. And we call that as a network digital twin. Now, a network digital twin allows you a sandbox for experimentation and running of what if scenarios, which you can then use to optimize your RAN. The problem is that there are so many parameters in RAN sphere that we don't know which ones to optimize. So to simplify that, there is another computing paradigm, which is known as intent based networking paradigm. So I only need to specify an intent that I want to minimize energy consumption, I want to maximize throughput, etc. These could be defined from users in terms of its business goals or business objective in terms of intents, and these intents need to be somehow using machine learning AI translated into scenarios which entity can understand, can have a context specific information, and then the network digital twin needs to be connected to application specific digital twins as well, so that you have application specific understanding of what the network is going to service. And then you can have a RAN which basically takes this entity implementation and then translates it into actual deployment scenario. Now, how this whole thing works, we have proposed a framework which again we haven't published this yet, but the idea is that we'll have this sort of a three-tiered framework. So you will have a top tier which is intent-based controller, which basically monitors the high-level business intent and translates it into scenarios. And then there is a northbound interface from NDT, which takes these scenarios and converts into semantic aware scenario planner. So basically you look at this scenario and you look at the context in which this scenario needs to execute, and then basically use this to generate a machine learning code in the cognition plane. Again, in here you can use things like application template libraries to generate XApps. And what we are proposing is generating, rather than writing these XApps, generating these XApps automatically, and then deploying these XApps onto a digital twin, which are application specific. And once you emulate actual application and how a particular XApp, for example, traffic steering or interface alignment is performing, then you can look at a certain KPI which you get by executing such an XApp and look at the statistics coming out from this XApp. And based on those statistics, you can have basically updates using reinforcement learning, for example. So you can have a model update planner or active learning element to it, which basically updates the XApp itself. And once your XApp is ready for pre-deployment, or you think it's ready for and basically you've done the pre-deployment or optimization, this XApp can go and basically through actuation plane can be deployed into RAN itself. And in this way you have sort of optimized things before even seeing that particular scenario. Again, you can assimilate data from the RAN itself. So you have a data plane which has semantic filter and preprocessor and performance analyzer, which feeds into your cognition plane. So you are trying to combine your live network data as well as your scenario planner, which is being fed into by your use case specific digital twin as well. So this is a bit of a complex architecture, which I won't go into too much detail because of lack of time. But the key idea is that you have intent-based controller, you have network digital twin, and that digital twin basically implements XApps and RApps. XApps and RApps have nothing but, as you will see in the next slide, have policies over certain interfaces. So you can see here, for example, and these policy values can be generated using machine learning. Now, how these policy values can be generated using machine learning, again, you can exploit things like TinyML, although TinyML is very popular in the context of IoT, as you will see in the reference below. But you can use the similar sort of, models to generate these numeric values for different policy interfaces. And then you can use application templates to generate these accepts autonomously. So this is what we are trying to build in terms of ORAN scenarios. So once we have built this, the next thing which we want to do is, enable certain use cases. And in our case, we are interested in 3 different use cases. We are interested, as I said, we have a project on a robotic swarm-based inspection of underground infrastructure. And while we do this as a standalone feature today, we want to look at subnetworking capabilities in 6G networks using ORAN architecture to enable such infrastructure inspection. Again, 3D co-design in metaverse type of scenario is something which we are interested, especially from e-health type of applications. Smart farming or agri-robotics is another area. Luckily, University of Leeds own its own farm, and we have a lot of space to do experimentation outdoor. So we are trying to deploy ORAN systems in these sort of environments, and then build rig applications using the framework which I outlined. So a little bit about, I'm conscious of the time we have, but a little bit about these applications. Okay, so let me give you a very quick introduction of what we're trying to achieve using swarm robots for buried pipe infrastructure inspection currently. See if I can go forward. Somehow it doesn't allow. Let me pause the recording and then try again. Okay, so this project is mainly about developing small robots which can go into underground infrastructure and then basically sense things like leaks, quality of health of the pipe, etc. And we have several different themes, including, a theme on sensors, a theme on robotic autonomous system, and there is a theme on communication and power, which I co-lead with my colleagues at Leeds. And again, you can go on pipebots.ac.uk and you can see all different types of work which we are doing in this area. But from wireless connectivity perspective, our vision was that we will build a underground robotic sensor network using these mobile robots in a hierarchical manner in a very harsh to reach communication area, and then we'll somehow connect it to the overground network. And obviously we want to extend this vision using ORAN, especially with subnetworking capabilities. You can build these networks as a subnetwork and deploy a lot of machine learning based tasks such as offloading of SLAM on the edge gateway itself as well. Just to tell you that this is not all theoretical, but you can also do a lot of interesting mathematical analysis of this such networks. So what we've been looking at is that if you have networks which are constrained to a particular type of topology, and then you're trying to plan how these networks should move, how they should be deployed, what sort of communication modalities you can create. You can cast them into a generalized random graphs, or from those of us which come with stochastic geometric background would appreciate that we can try and formulate these problems in a stochastic geometric manner to a certain extent to understand the dynamics and the parameter of the network itself. The second application which I mentioned very quickly was agri robotics application, and we had a project which was funded by STFC where we were looking to basically augment a robot with a gamma ray sensor to do gamma ray spectroscopy to measure the soil quality. And to implement this system, we use cloud native implementation in any case. So what we're trying to do now is migrate this to Open RAN architecture, again using same sort of a framework. Now, as you know, we are dealing with robotics and autonomous system application. We can build a digital twin of such a system or such a farm system using GIS models, which we already have. We can also build a digital twin of the robot itself using things like Gazebo and ROS, and we can export some of the parameters from there, build a physical model as well. So we can build an application-specific digital twin, which we are currently building in our group. But it would be good to have a network digital twin and then connect this digital twin with the network digital twin and look at the connectivity requirements as well as through the framework, which I outlined briefly in my talk. The third area, we are not looking at metaverse sadly yet. We are looking at something which is more healthcare related and again funded by EPSRC Network Plus. We are looking at wearable sensors and how we can get data off these wearable sensors using 5G technology, for example, where we can enhance the lifetime of the sensors itself or deploy 5G only sub-networking capabilities only on the edge devices themselves. And here the main motivation of implementing it using a subnetwork rather than a traditional IoT network is mainly that we can do things like federated learning and execute the federated learning loads within ORAN architectures very easily. Okay, so overall summarizing what I've discussed so far, the evolution of RAS itself, we said that there are 4 components of our robotics and autonomous system. 2 of them basically, which is the brain of the RAS, is mainly being offloaded into cloud, and the cloud robotics or cloud RAS is becoming one of the key research areas where communication and connectivity plays a vital role alongside compute infrastructure as well. What does the cloud robotics scenario enable us to do by bringing all these open APIs, huge amount of data sets, collective learning, sharing of this knowledge? We can enable new breed of robotics and autonomous system applications. However, we are increasingly reliant on the connectivity, and this connectivity is required at a very low latency. So thus we talk about ultra reliable low latency communication or extremely low latency communication for robotics and autonomous system. Okay, I won't go into the research challenges which exist at this. I mean, most of us are familiar with this, but you can read it on your own time. I would like to, in the interest of time, I will use last couple of minutes to cover some topics on how robotics and autonomous systems are servicing communication and networking capabilities. So one of the key elements of robotics and autonomous system is that unlike traditional networks where you have no control over mobility, in the context of robotics and autonomous system, you have controlled mobility. So we can exploit the controlled mobility to provide better connectivity in a sense. And this phenomena is known as mobility diversity, which we came up with a few years back. So just to give you a very simple example, if you have a mobile robot, there are lots of obstacles trying to communicate with a base station. Possibly there is no line of sight and there is a multipath environment. How should you move so that the connectivity is optimized? And we looked at this problem by considering a holistic framework whereby we model the robot, we model what are the key components, and then we look at how should we exploit this knowledge of channel autocorrelation functions, for example, so that we only transmit in areas which have higher chances of getting communication through at a given quality of service constraint. Again, these are the references where you can read more about the algorithms which we employ to enhance. And recently, my ex-PhD student Daniel has also written a tutorial article on how mobility diversity can be used to design controllers for robotic systems which are communication aware. Another area which is really interesting in RAS for communication is drone-based communication. Again, there are lots of different use cases. I won't go into detail, but within my research group, we have been trying to look at things like how do we deploy a drone-based communication, not only to service traditional users or UEs, but also how can we enable practical drone-based deployment for backscatter type of IoT sensor networks. And again, this presents a lot of interesting opportunity as well. Um, uh, uh, Basically, what we try to do is model the networks using a stochastic geometry and then look at the optimization, given our expertise in this area. Um, Again, I will leave you with some references and not go into the details. But what we also tried to do was to build these RF backscatter sensors ourselves, which are coin cell operated, can last for several years, recycle energy from the ambient environment, and then basically we offload the task of providing energy to drone itself. So we have deployed these sort of sensors in agricultural application where we are doing soil moisture sensing, for example, and then transmitting that using backscatter sensors. This is again an exciting area, and given the amount of interest in community in risk as well, naturally aligns with that as well. Again, you can see a lot of information on what we have been doing on these URLs as well. Lastly, we looked at more sort of a futuristic backscatter applications, like embedding these backscatter devices in a wearable e-textile. How do we incorporate both sensing and communication elements into such modalities as well? So this is something which we are exploring in my research group as well. Lastly, I would like to conclude this talk by having a call for collaboration. So as I said, I currently co-lead one of the future communications hub on cloud and distributed computing. And there are sort of 3 or 4 different pillars of this hub. So we are looking at the networks from emergent systems perspective, sustainable systems perspective, and then human-centric perspective as well. And we're looking at a lot of new key performance indicators as well. And most of these things I've discussed in this talk, so I won't go through in much detail. But this is more for colleagues who want to collaborate with us on these different topics. So please feel free to reach out to me on any of these topics, and then we can align with other hub members. So we are about 6 universities and about 27 odd academics. So I can point you to the right person doing a research in your research area. So with that, thank you for being patient today and listening to me. I hope what I've realized that the 45 minute was too small for this talk, but I hope that I've communicated some of the core ideas and some of the core research directions, which there are lots of opportunities in. And more than happy to take any questions. Sadly, I can't be on the Zoom meeting today because of another commitment. But if you want, you can email me your questions, and I'll be more than happy to reply to them. Thank you.